Bismillah ar-Rahman ar-Rahim. Today, we are going to discuss what we call don't care conditions in KMAP. Okay. Sometimes from the problem description, you can understand that part of the input, okay, let's say that your input is 3-bit, okay, and from the description of the problem, you know that, for example, let's say input 101 will never show up, okay, it will never show up in the input, okay. So we call this input here, we call it a don't care input, and the output is going to be a don't care condition, okay. So meaning that we don't care about the value of the function at this given input, which is a don't care condition, okay. We don't care whether the value here is 1 or 0, because this input here is or belongs to the don't care conditions, okay. So for example, let me give you a practical example here. If, for example, you are expecting, first of all, let me just make sure that you can hear me, guys.
Yes, we can hear.
Okay, cool. Okay, good.
Yes, we can.
Good to know. So let's say that you have, you are expecting a BCD input. Okay, BCD input. What is BCD? It's binary coded decimal. Remember, it's binary coded decimal. So it's a binary number that is coding a decimal digit, right? And decimal digits range from what to what? 0 to 9, right? So your binary coded decimal, as we learned in unit 1, is 4-bit. You remember that, right? It's a 4-bit number that can go from 0 to 9, okay? That can map or encode the decimal digits from 0 to 9. So it goes from 0, 0, 0, 0 all the way to 1, 0, 0, 1, right? This is BCD 8421, right? And you know, if your input is a BCD, you know that you will never ever receive any input outside the range. What do we mean by outside the range? We mean the numbers, the other patterns in the 4-bit binary numbers. We mean 1010 up to 1111. Okay. So your range, your valid range, is from 0000 all the way to 1001. Okay, this encodes 0, decimal 0, and this encodes decimal 9. So you can safely assume from the problem description that inputs 1010 all the way to 1111 will never show up or occur in the input, okay? This is given by the user, and if it does, then it's the user's problem, not ours, okay? And hence, thus we can call these inputs, we can call these input patterns don't care conditions, okay? Because we don't care about their values, okay? We don't care about the output during the occurrence of these inputs, okay? And we take advantage of this fact by picking the values of these inputs, of these don't care inputs, okay? All right, we pick the values of the output at these patterns to minimize our function further, okay? To simplify the function further, whether they are zeros or ones, okay? Let's take a concrete example. Let's take a concrete example and see how we can proceed. Now, we are going, in this example, we are going to use all what we learned, okay? In addition to some design capabilities, okay? So in our example, we would like to basically design a logic circuit, all right? So our end product here is a logic circuit, okay? that what? That generates an odd parity bit of its BCD 8421 input. Okay, so from the problem description, what do you understand? We would like to design a circuit, right? Black box circuit, C. Okay, what does the circuit takes? Input is I need you to be more, active in the class, guys. Okay, otherwise I will be bored like you, just like you. Okay, so please answer my question. What is the input to this circuit from the problem description?
BCD code.
Yeah, BCD number. Okay, BCD. All right, and what is the output? You can see the problem description in the top.
Odd parity.
Yeah, so it's an odd parity. Let me just emphasize it. An odd parity. Of what? Of the input BCD, okay? Do you guys still remember what an odd parity is? What does it mean?
Yes. Yes. Odd number of
Who
ones.
can remind us? Yeah, go ahead, remind us.
Odd number of ones, I think.
Yeah, so you generate an additional bit to the BCD such that the number of ones, the total number of ones, including the parity bit, will become what? Odd. Excellent. Okay. Okay, so almost we have specified the input and output, but still input is not fully specified. BCD, what does it mean, BCD? Means
binary code.
Come again?
Binary code.
Yeah, binary code. What does it mean in terms of circuits? And think about it in terms of circuits. Input, an input is a wire, right? So how many wires are here?
4. 3.
4.
4.
Excellent. So I need to name them. They are inputs, so they are variables, right? So I need to name them, like, for example, Y3, comma, Y2, comma, Y1, comma, Y0. Okay? And the output is how many bits?
5.
5 bit.
Including
Okay.
the
We are generating only the odd parity here. Concatenating that with the input will be something else. Okay. I actually don't need the circuit for that. It's just a matter of bringing this in together with this. Okay, just an extra wires. Okay, so my output is how many bits?
Just 1.
1, which is P. I'm going to call it P. Okay. Now we need to list the input. Okay, the possible inputs and possible outputs. I mean the corresponding possible outputs. What do we call this thing here? The structure?
Truth table.
Excellent. We need to formulate a truth table for the problem. Okay, so the truth table for this is as shown here. Okay, and you can see that there is a parity bit for all the inputs up to from 0 to 9, but from 10 to 15, since we are expecting a BCD number, we don't care about the parity here because we will never ever receive an input from this range, and if we do, it's a user's problem, not ours. Okay, it's the whoever is feeding the circuit problem. Okay, so now let's see if my calculation of the parity is correct or not. Okay, before I do that, just to show you another shorthand notation for doing this table instead of listing all the 16 values, I can do it this way, from 0 to 9, and then put the parities here, like here. Okay, and then from 1010, which is 10, up to 1111, all the values are X. Okay, I don't have to replicate them like this. Okay, this is enough for me to understand that these are don't care conditions. Okay, all right. Now for 0, 0, 0, 0, what is my parity bit?
1.
1. Excellent. Why? Because this is what makes the total number of ones in the whole thing become odd. Okay. All right. Let's pick another one. 0, 1, 0, 1. Does it make sense that the parity is 1 here?
Yes.
Yes.
Okay. What about 0, 1, 1, 1? Does it make sense that the parity bit is 0?
Yes.
Yeah.
Yes.
Anyone is challenged by the calculation of the parity bit? Remember, it's an odd parity bit. If you don't, be honest. Please be honest and tell me so that I can explain it. Otherwise, I will assume that you understand. Okay. We have a chat message. Let me just see it. Okay. So the odd parity bit, okay, the objective of the odd parity bit, okay, is to make sure that the total number of ones in the output plus the inputs is odd. Okay, if it was an even, then the total number of ones must be even. Okay, so now this is my output, which is the odd parity. Okay. And my input is 0, 0, 0, 0. How many ones in my input? How many ones in my input? Let me just, yeah, Ahmed Mbarak. How many ones in my input here? Ahmed. None. So it's even, right? It's even. 0 means even. 0 is an even number. Okay. So my P here is 1 because I need an odd parity. Do you get it? Let's take another example. 0, 0, 1, 0. How many ones here? Yeah. So Ahmed is saying, so if it's even, it should be 1. The answer is yes, because we are generating an odd parity. If we are generating an even parity, it would be the other way around. Okay. So if I ask you, yeah, Ahmed, okay, what is 0, 0, 1, 0? How many ones here? It's just 1, 1, and 1 is an odd number of ones. So I don't need to add another 1 to make it odd. So my parity is 0. Okay. The parity is 0. And let's take another example. 1, 0, 0, 0. There is 1, 1 here. So my parity is 1. And 1, 0, 0, 1. We have 2 ones here. So in order to make it even, in order to make it odd, we have to make the parity 1. Okay, good, good, excellent. Do you get it, Ahmed? All right, you're welcome. Although I prefer that you talk through your mic to save time, but chat is fine if you don't have a mic or your mic is broken or something. Okay. It's really anyway, let's just move on. Okay. So what is my next step now? Remember the problem description here. It says design a circuit. So my end product is a circuit. Okay. That generates an odd parity of its BCD 8421, right? So what is my next step? I'm going to give you a hint. What is this unit is about?
A K-map.
Yeah, so we need to do a K-map, okay, for this output here in order to find the simplest form of this output in terms of the input, okay? So let's do it here. So I just copied the truth table here. so that we can generate the K-map. Okay, so here is my K-map. Okay. And this is y3, y2, y1, y0, okay? Further, we have the annotations, y3, y2, y1, and y0, okay? All right, now where are the ones of the function? We have a 1 at 0, and then a 1 at 3, and then at 5 and 6, right? And then at 9, right? Okay. Now comes the cool thing, okay? The remaining part of the K-map are X's, okay? So from 10 all the way to 6 to 15 are all don't cares. So I can pick them however, okay, I want, such that my function is as minimum as possible. Notice that if I don't have, I don't care if if I just choose them to be zeros, okay? Can you group anyone with any other one?
No.
Yeah, so it's your function will become a sum of min terms, okay? Which is which will have how many literals in this case?
5 literals.
5 times 4, actually. 5 times 4, which is 20 literals, okay? So 5 min terms, but every min term contains 4 literals, and that's 20 literals in total. But luckily, we have these don't cares here to help us get rid of some of the literals. Okay, so just to get you started, I can, for example, consider these x's as ones, these ones here. Okay, such that I can group this together here. Yeah? And this one here is nothing but, this is my function here. My function is going to be, is it P? P, I think, yeah. It's P is going to be y3, y0.
y0.
Excellent. Ordered with, yeah. What is the next one? Come on, guys. We have a lot of choices here. Okay.
6 and 14.
Yes.
6 and 14. Excellent. Okay, 6 and 14, and this corresponds to what? It's y2, and it's outside. It's inside of y1, and it's outside of y0. So y0 complement, ordered with, okay, 5 and 13. Yeah. 5 and 13 is simply y2, yeah, and it's inside, it's outside of y1 and inside of y0. Okay. Next.
11 and 3.
Excellent. Yeah, 11 and 3. You are getting you guys are getting expert in K-maps. Okay. So what is 11 and 3?
y0.
What is 11 and 3?
y0 and
y2. Let's start with y2. Okay, y2 complement. Okay, what about y1? Is it outside or inside? It's inside, yeah. And y0, it's inside. right? Not or. It's sorry. Did I just click? Oh, okay. It's so y2 complement, okay? Y1 and y0 is again not complemented, okay? The final one, okay, is what?
0 and 10.
0. Can I group it with any other? No. The answer is no.
Ah,
Okay, answer is no, because remember that this one is not adjacent to this one, but the whole corner you can take together, or this with this, or this with this, okay, but not this with this, okay, because two variables will be changing if you just group these, okay. Yeah, so what is m0 now? M0 is nothing but the complement of all the variables. y1 complement, y0 complement. Okay, so this is your function. Okay, this is your parity function, and you just need to convert this to an and or circuit. Okay, to continue the answering the question. Okay, so how many AND gates do you have here? 1, 2, 3, 4, 5. And how many OR gates? Just one. How many inputs for the OR gate? 1, 2, 3, 4, 5. 5 inputs. Okay. So this is nothing but a sum of product standard form, which is basically an AND OR implementation, two-level implementation. Okay. All right. Any question?
clear.
Clear. Okay. So now I'm not going to discuss 5 and 6 variables in the class. 5 and 6 variables came up in the class, but I'm including the slides for your reference. Okay, the slides from Dr. Mudawwar's presentation. Okay, they are an excellent slides, by the way. All right, so go over them to see how 5 variables and 6 variables came up are simplified. And if you have any question, you can come back to me and we can have an office hour to illustrate that. But you will never have a question in the exam about this. We have never made an exam about this. It's not difficult. It's just tedious. Okay. I mean, drawing 6 variables came up. How many squares do you need to worry about? 64 squares. I mean, this is too much for a human being. It's okay for a computer to do, but a human being, okay, it's just boring. Okay. All right. With that mentioned, okay, we move on to unit 6. Okay, which is basically about the other gates. Now we are going to elaborate more on the gates that we studied very briefly before. Okay, buffers, tristate buffers, NAND NORs, XOR XNORs, and the parity generation and checking circuits using XOR and XNOR. Okay. Okay. So let's start with buffers. Okay. So buffers are not used for functionality. The buffer basically, the buffer gate takes the input and replicates it at the output. It doesn't change the input at all. So the output equals the input. However, it's used for amplification of the signal. Okay. So if your output is expected to drive many gates at the output, like here, for example, okay. So let's suppose that we have this AND gate that is driving these three OR gates. Okay, it can be possible. It is possible that that this AND gate is probably not capable of driving, or the output here is not capable of driving all of these gates here. Okay, so for example, what happens here is that we have a fan out here, fan out branches. Okay, fan out branches means that the current is going to be split among these branches. Okay, and maybe just maybe that the current is not enough to drive this gate here, or this gate here, or this gate. So and the result is going to be a malfunction in the circuit. Okay, so the solution to this, in order to make the circuit or the output strong enough to drive the other gates, to give it driving capability, is to include a buffer. And the symbol for the buffer is similar to the inverter without the bubble. So the inverter is represented by this symbol. Okay, notice the bubble here. However, the buffer is represented with this symbol. Okay. So now the buffer is strong enough. We assume that the buffer is going to give the signal the enough strength to be splitted among these three fan out branches. Okay, so the main reason for using the buffer is to amplify the signal. Here is another example. For example, if you have let's say that you have a signal. Okay, let me just redraw this from beginning so that it becomes clear. Okay, so suppose that we have an output here, some output. So it's coming from, let's say, an AND gate, for example, and then this output goes also to three branches here. Each one of them will drive another gate. Okay, so for example, here you have an AND gate, here you have an OR gate, and here you have, for example, an XOR gate. Okay, and we don't care about the gate. We just say that we have three gates, and then here we have another fork in which we are driving other gates. So a total of 6 branches. In this case, if just a single buffer is not enough, okay, then you can also have a buffer here as well as a buffer here. Okay, all right. So a buffer for pair, for example, 3 output. Okay, and maybe just maybe that you have a buffer here as well. Okay, if for example the output is not strong enough to drive these buffers. Okay, so they are acting on like a tree structure. All right, so what is the advantage of the buffer is that it is providing the required strength, the required drive capability for driving larger fan out branches. Okay, however, the disadvantage of the buffer is that it creates what we call a propagation delay. Okay, propagation delay. So it contributes to the propagation delay of the circuit. Okay, so it is an actual gate. Okay, although it doesn't change the functionality of the circuit. However, it's an actual gate. It has an input and it has an output, so it has a propagation delay itself. So it affects the propagation delay of the circuit. Okay, so this is all about the buffer. Any question about the buffer? Or shall I move to tri-state buffer? So when do we use the buffer? Anyone can answer. When do we use the buffer?
To amplify the signal.
Excellent. To amplify the signal. If you want to larger driving capability, then you use the buffer. Excellent. And by the way, the buffer has so many sizes. So eventually it depends on the size of the transistor inside the buffer. Okay, if the transistor is large, then it can have high driving capability. Otherwise, it doesn't. If it is small, then it drives only a small load. Okay, now moving on to tri-state buffer. Tri-state buffer, on the other hand, is a buffer, but with a third state. Okay, so we usually have in binary, we have only two states. Okay, 0 or 1. But a tri-state buffer has a third state in addition to 0 and 1. It has a third state, which is the high impedance state. So this buffer here, this tri-state buffer here, we can connect X to Y, okay, or the third possibility, so we can connect X to Y, so Y can have a 0 or a 1 depending on X. So these are two states. The third state is that when enable is 0. When enable is 0, it will disconnect X from Y. And Y, the net Y will become floating. Okay, so it's a high impedance node. Okay, it's in high impedance state. Okay, so Y is not connected to any other node here if enable is 0. If enable is 1, then Y is connected to X. If enable is 0, then Y is not connected to anything. So this is the function table here. So if enable, pay attention to this because we are going to use it in the examples later. If enable is 0, then this is high impedance. High impedance means there is no connection between X and Y. There is an open circuit, okay? If enable is 1, on the other hand, then Y becomes X. It's not a don't care here, it's a variable X, okay? Variable X, okay, becomes Y, or Y becomes X, all right? Now, any question? Sometimes we have a bubble here in addition to this diagram here, okay, or symbol. Sometimes we enable is also having a bubble here, okay, bubble to indicate that enable is inverted, okay, or it's an active low signal, okay. So in this case, when in this case here, okay, the function table will become like this, enable Y. So when enable is 0, Y will get X. When enable is 1, Y will get high impedance, okay. All right. It doesn't matter whether you put enable on the top or the bottom of the triangle. It doesn't matter, okay. So this is an active. We call this an active low control tri-state buffer, and this one is an active high control tri-state buffer. Active low means the signal is activated when enable is low, and active high means enable is or the device is activated when enable is high. Okay, high means 1. Okay. Any question? Let's take an example if you don't have any question. But before that, let's just convince you by an application of the tri-state buffer. So tri-state buffers are used in computers. Okay, for example, in computers we have what we call the central processing unit. Okay, and then we have what we call a bus. Let's call it data bus, for example. Data bus, okay, and then we have the memory. Just simplistic design here, okay. Now this bus here, this data bus, notice that the CPU, okay, can either write to memory or read from memory. So both the CPU and the memory will write to the data bus, right? So we have here an input-output, okay, input-output relationship, okay, but it cannot happen at the same time, okay. If it happens at the same time, we will have a short circuit and your system may burn, okay. So it's either the CPU or the memory will write to the data bus, and the other one will read later. Okay. So what happens when we what happens here in this connection and this connection? We have one option is to use tri-state buffers. Okay, tri-state buffers like this. For example, imagine that this bus here is 1 bit and it's called Y. Okay, all right, and this signal here, for example, is coming from the CPU, and this signal is coming from the memory. Okay. So and to control them, you use a control signal called enable. Okay, if enable is 0, then we output x0 on the bus. If enable is 1, we output x1 on the bus. Why is that? Why is that? And how that is possible? How is that possible? So now enable is the same signal on the top and the bottom. Okay, enable is the same signal. It's given the same name, so it's the same signal. So imagine there is a wire connecting both signals together. Okay, imagine that this signal here is connected to this signal here. Okay, they are the same signal, but I'm not showing it here to make the circuit look neater. Okay. Okay, so now when enable is 1, I have a connection at this buffer here, or tri-state buffer connection. So and for this buffer here, do I have a connection or a disconnection? When enable is 1.
Disconnection.
Yeah, so this one here is disabled, basically. This buffer here is disabled or disconnected. So the only connection that I have is x1. So Y will get x1. All right. And then Y will be consumed by other components. Okay. How about if enable is, so when enable is 1, I get x1. And when enable is 0, here, this one is going to be disconnected. And this one is going to be connected. You see that? So I get, when enable is 0, I get x0. Do you see that? So now enable acts like a control input, which is basically which selects either x1 or x0 depending on its value. Okay, so this circuit is nothing but a selector, or what we call later we'll call it a multiplexer. Okay, so just to rephrase what I just said, okay, the top tri-state buffer will bypass x1 to y if and only if enable is 1. Okay, and the bottom tri-state buffer will bypass x0 to y if and only if enable is 0. Okay, note the bubble here. Okay, note the bubble. All right, bubble makes a big difference here. Okay, but let's suppose that we don't have a bubble. What will happen?
We'll have a short circuit, as you said, and
yeah, what does it mean, a short circuit? Let's just try to understand electrically speaking. Okay, so we have here x1. So if we don't have, now I'm drawing the circuit if we don't have a bubble for the bottom tri-state buffer. So we have x1 here, and the equivalent circuit is going to be like this. And here it's x0. So both of the circuit, both of them, if enable is 1, are going to be connected. And this is my y. Let us suppose for the sake of discussion that x1 is logic high or logic 1, and x0 is logic 0. Okay, what happens now? The signals will fight over the line. Okay, one is saying no, it's logic 1, and the other is saying no, it's logic 0. Okay, now if you have a system like this, we can model, can have here, we can imagine that we have a resistance here, which is 0, okay, because it's just a wire, okay? What is the current that is passing through this resistance here? It's going to be V1, the voltage difference, the current I, okay? It's going to be the voltage difference between the two nodes, okay, divided by the resistance, right? V1 minus V0, okay, divided by 0, which is infinity, okay? This is what it means, and this is why you may burn your circuit, because you'll have a very, of course, this is just theoretical, okay? Infinity is theoretical, okay? In practice, you'll have a large current, okay, which will burn your components, okay? Do you understand now the importance of having the bubble here? Bubble here is meant for that no two inputs are competing for the usage of the what we call the wire, okay, or the shared bus here. Okay, any question?
Doctor.
Yeah.
If we have multiple components, how we deal with it?
Here we are having multiple components.
يعني bigger than 2.
Yeah, then you have to use more than so let's, this is an excellent question. Let's say that you have 3 or 4 components, okay? 4 components, and you'd like to connect them to the same wire, okay, using tri-state buffer. All right, then what happens is that you need to select one of the 4 components, right? So selecting one of the 4 components, what does it mean? It means that you have to have 2 bits for the selection, right? So my enable will be 2 bits now, my enable 1 and enable 0, okay? So it can be 0, 1, 0, 1, and 0, 0, 1, 1. Excellent, okay? And then the output, which is Y, will be X 0 if we have 0, 0, and X1 if we have 0, 1, X2, and X3, right?
Yes.
So what happens is that we have what? So we have 4 tri-state buffers here. All right, 4 of them, and here in the enable of this, what do we get? This is X0, let's say. Enable of this will have EN1 complement ANDed with EN2, EN0 complement, okay? Yeah? And for this one, for X1, so all of them are connected to the same output here, which is Y, okay? And for X1, it is going to be what? Just the min term. What is the min term here? EN1 complement ANDed with what? EN0.
EN.
Yeah?
0. Yes.
Yeah. So we are implying an AND gate here, okay? But I'm not drawing it, okay? And for this one, what is the function here?
EN1.
ANDed with?
EN0 complement.
And the final one?
EN1, EN0.
Yeah. Do you get that now? X2.
Yes, thank you.
X3. So depending on the values of enable, which is 2-bit now, you will get one of the inputs. Okay, for example, this is coming from the CPU, memory, and etc. Okay, so if you have more than peripherals, for example, and stuff like that, mouse, keyboard, whatever. Okay. Did we cover everything? Yeah, next we will discuss the NAND gates. We'll start discussing the NAND gates. But this is an excellent example. Thank you for asking. Who was the one who asked, by the way?
Yes.
Let me just Muhammad. Okay, excellent. Okay, so let me stop recording so that the lecture doesn't become longer than required.